Yeah, and let's talk about being lazy today. All right, we've had a busy semester, and so now is the time to relax and be lazy and talk about lazy functional programming. All right, yeah, switching gears right away. Yes, so let me talk about what is lazy versus eager evaluation. So before I do that, let's take an example. So let's take this strange function, uh, this function which takes in, let's say, two arguments, x and y. Okay, and let's say it does the following. So it returns a number as well, and let's say if x is greater than or equal to 0, uh, it's going to return, let's say, x minus x times x plus x mod 2. Else, let's say, it just returns y. Okay, so that's a perfectly respectable function. All right. And we could call this function on something like this. Oh, and let's also print. Whenever you call the function, let's print what we are doing. So let's print that I'm calling func on x and y. So I'm going to print the arguments. Uh, so far nothing surprising, right? So let me compute some value. Z is func, I don't know, 10, func 15, 45 minus func 12, or let's call it minus 12, and func 30, 24. All right. So now that you have taken programming languages for the entire semester, take a minute and tell me how many times is this function func going to be called, and what are going to be the arguments of each of those calls. So what would be the first call you get to func? What are the parameters for the first call? Then tell me the parameters for the second call, the third call, and the fourth call to func. All right, anyone? Okay. Um, yes, the evaluation order is from left to right. So four calls, excellent. So the first call is func 1545. So Reagan, you get like the first, and today we are going to call the people who are going to answer first, the eager. Uh, so the eager people, all right. I'm not going to say eager what, but so the second call is going to be, wow, someone's really good at calculation. So someone needs to needs to get faster than Reagan here. She's getting faster than my computer. That's right. So the first call is this one, func 1545. The second call is this one, uh, func 10 something else. And what is the third call? You might as well go ahead, Reagan. Okay, 3024. And then fourth call, 3034. Very good. So that's what happens. And you might as well see this. The fourth call would be minus 12 minus 870. This one, minus 12 minus 870. And this is 24, not 34. Is that okay? So four calls to this function. Does this make sense? Okay. So however, take a look at this function. So in this function, if x is greater than or equal to 0, if x is greater than or equal to 0, then I compute something involving x, but no y is involved here. On the other hand, if x is less than 0, I am using the value of y. So if you look at this first call, func 10, you notice that this inner call, func 1545, is useless. Why is that useless? The call that I'm highlighting, func 1545, is a value that gets computed but never used. Why is that? Yeah, exactly. So 10 is greater than or equal to 0. So because I'm calling with x greater than or equal to 10, you are never going to need the value of y here. Okay. Uh, on the other hand, in the second function call, you do need the value of this call, right? So even though we have made 4 function calls to func, you just need 3 of them. You don't need all 4 of them, right? 3 of them would have sufficed to carry out this computation. Sounds good? But The semantics that we are using is called eager semantics, eager semantics. And that's why I called the first person who came back as eager, because this is called eager semantics. What does eager semantics mean? We also call it call by value semantics, same thing. Okay. And what does this mean? This means that if I have an argument to a function, so evaluate all the arguments to a function before you call it. So therefore, if you wanted to call this function func10, the arguments are 10 and func1545, then before you can call this outer func, you have to evaluate the inner argument. So you evaluate 10, which is trivial, that's just 10. You evaluate func1545, you get these two values, 10 and minus 209, and therefore you have function called on 10 and minus 209. It makes no sense to evaluate a function before you have all the arguments. Good so far? However, we are going to study something else today. So we are going to study lazy computation. So the principle behind lazy computation is compute something only if you're going to need its value. Do not bother computing things whose value is not being used anywhere. So you would only compute things when you are going to use its value or when you're going to need its value. All right. And that is the main principle of lazy computation as opposed to eager computation. So in eager computation, you're going to compute things differently. So Laura raised something amazingly insightful. Yes, it is kind of like short circuiting, except that short circuiting is something we use only for and or for very strange reason and don't use it for anything else. But today we are going to use it for everything. All right, so we are going to try and put short circuiting as a first class thing, right? Try and get short circuiting for more things. Right? So that's the idea here. The idea here is don't compute things that you're not going to use. So you only compute things that you are going to use. Okay. Now, interestingly enough, lazy functional programming is very, very difficult. It's very hard to reason about. It's something that many languages will not support or will support, but will give you very poor support for it. Fortunately for us, Scala supports lazy evaluation, so we'll talk about that. All right. Okay, so we'll do that, and so we'll talk about that. So there is a question from John. What did we call the y in the first function call? The second argument. Oh, it's called an eager evaluation or an eager argument, right? Or call by value. Is that what you're looking for, John?
Yes, but I think, did we call the y in the -12 func?
Mm-hmm.
I forgot. Did we call it a useless value, or was that just not? Was that any semantics we need?
No. So,
Okay.
so let me explain. So in the very first call, x would be 10 and y would be whatever func 1545 was. Turns out this y, the func 1545 is useless. We don't need it. It's never needed, right? Whereas in the second one, this y, func 3024 for the second call is actually needed. So all we are going to say is this is being used. So in the second call, all the arguments are being used. In the first call, only the x argument is being used. As if you can follow my highlighting, the second argument, the y argument, is not being used. That's all. That's not a technical term. That's just my English way of saying it's not being used, right? Is there any name for a useless value? Well, we don't call it useless. We just say it's a value that's never being used. Yeah, I mean, useless passes some value judgment to things, right? So I don't want to say that. But it's something we are going to optimize away. Okay. All right, very good. So where was I? So let's talk about how we are going to do this. So Scala gives us what we will call second class support. So there is a way in which I can take the default behavior in Scala, which is eager, okay, eager evaluation, And I am going to, you can change the default behavior in some ways and make it lazy. And I'm going to show you ways to make it lazy today. Uh, there are some languages where lazy is the first class semantics of those languages. And there is a language called Haskell, which is a pure functional language, which uses lazy semantics. So people who want to really learn functional programming to the, at its deepest, at its purest, learn Haskell. It's a rather popular language among many computer scientists. You would find a lot of tutorials. I recommend a recent book called Learn Yourself a Haskell for a Great Good. Yourself a Haskell for a Great Good. So written by someone from Hungary. I really enjoyed reading that book. It was a lot of fun. They tried and to make Haskell really fun. But Haskell is like the language that the purists would use. I myself don't use Haskell too much, but it's a language that I try and learn sometimes when I have, when I'm bored. All right. So let's do the same thing, but now I'm going to do it in a different way. So I'm going to write the same function, but I am going to write these parameters in a different way. And I'm going to put an arrow in front of these parameters. And when I put an arrow in front of these parameters, the arrow says that X and Y are call by name parameters. What does call by name mean? So let me explain again. So now I have redefined func to do call by name. Okay. So John has an excellent question. Don't we possibly lose side effects? We will, and it's going to become really strange if you have side effects. So you typically do this for things without side effects. Yes, Sean, that's exactly what I was talking about. This book. Uh, yeah, learn you a Haskell for a great good. It's actually really fun. You would find a lot of these things are actually familiar from you reading Scala. So I actually really would suggest you read it. So you will find a lot of things we covered in this class are in Haskell. So you can see there's something called a map, fmap. Uh, you'll actually learn it in a different way. So that's the fun thing. All right. Anyway, where was I? Yes. So let's talk about lazy evaluation. The entire language of Haskell is built on lazy evaluation. Okay, and what is called call by name. So I'm going to talk about call by name. In Scala, you can force call by name by putting an arrow in front of the parameters like this. So when I say x is of type arrow int and y is of type arrow int, this arrow is not a type. This arrow is just an indicator that these parameters x and y are being passed as call by name. Okay, let me give you an example. Let me write a function called g, which just takes in a number and returns a number. And let's say g is x plus 1, but let me put a print statement. So let me just put a print statement here and just return x plus 1. Okay, so let's just do this. And let me call func now. Let me call this func by name. Okay, func by name, func by name. And then let me call, instead of the first parameter as x, I'm going to call g of 10. And the second parameter, let me just do 12, something like that. So this is just very simple. Func by name is, I'm just going to call x to be g of 12, g of 10, and y to be 12. All right. Now, let me do the same thing and let me call the old function func. Let me call that as well, g of 10 and 12. Let's see what results we get. So let me call val x1. Let me call this val x2. Okay, so far. Now, can everyone predict when I call func, the old function func on g of 10 and 12, how many times will g be called? So this is nothing strange. This is this old function func xy, okay, call by value, and I'm calling func g of 10 and 12. How many times do you think g is being called? Exactly once, right? Okay, no tricks, right? Thank you. That's correct. That's correct. So g of 10 is called once because you call it once to evaluate the argument, and then you're going to be done. Now comes the fun part. When I call func by name g of 10, how many times is g going to be called? So what happens here is in call by name, I do not evaluate g of 10 when I call the function. Instead of x here, I pass g of 10. Yes, very good. Let's talk about it, right? So instead of x here, I just pass g of 10. Every time I need to evaluate x, I will need to call g of 10. So it will be called once when I'm printing x, twice when I'm comparing x to 0, third time for this, fourth time, fifth time, sixth time. So in my reckoning, it will be called 6 times. No, once for printing. Okay, so once for printing, because I'm printing it, right? Remember, this printing is printing, right? So you have to evaluate it while you're printing it. Once for the comparison, uh, third time, fourth time, fifth time, sixth time. Good. All right, let's see. And that's what call by name does. 6 times. 1, 2, 3, 4, 5, 6, 7. Why seventh time? Because I think there is another print statement somewhere. Uh, let's get down to the bottom. Oh no, no. This first time is not counted. So this is for our old one. 6 times. All right. So 1, 2, 3, 4, 5, 6. Good. Yeah, so this is going to be bad for efficiency, right? But this is what call by name semantics is. It's an ultimate form of being lazy, right? And being lazy is bad for efficiency, right? So whoever said that being lazy is good? Aha. So Jacob has a great idea. Here's Jacob's idea, right? So why not? Let's call val x1 equals x, and then use it. So x1, 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 x1. Okay. So that works. So you can do that. And in fact, if you did that, then you're going to get back to calling g exactly once. Good. Yes. So call by name is going to be different from call by pass by value, uh, and pass by reference semantics is not quite done in Scala, right? So you can't pass things by reference. You do it in a different way in Scala. Instead of passing things by reference, what you would do in Scala is you would wrap it up in a class uh, X, and then you would put a var in there, and then you would pass a reference, you would pass this outer class X by value, which will pass it by reference. Okay, so call by reference in Scala is not first class, it's not supported, but it messes up with call by value. But ultimately, it returns the same answer unless your function g has side effects. If your function g has side effects, then yes, it won't return the same answer. Right? So you want the g to be like whatever you're calling in your call by name function, whatever expression is here should not have side effects. You should not be using a var. You should not be updating global states and so on. If you have side effects, then you're going to create a different answer. Okay, so far. Now comes the second part of being lazy. So you may say, this is fine, right? This is fine, but how do we solve the issue that, let us say I need to use y twice. Let's change the function here. So how do we do this, right? So I could do this, and I could say val y1 equals y, okay? And I could say calling function $x1 $y1, and I could say y1 times y1. But I am back to where I started, right? I wanted to come up with a way to write this function where the value of y is only used if it's ever needed. But here I am coming up with ways in which I'm going to. So this is going to force X to be evaluated, and this is going to force Y to be evaluated, right? So for example, suppose this was G of 10 and G of 12. Now you will still get G to be called twice no matter what, right? So you're going to call G twice, and then you're going to call the function. Yes, your idea is not a total wash, except that we now need to pair it up with a different kind of a val called a lazy val. So let me just comment this out, because this printing will cause things to break. But let me call this a lazy val. Okay, what is a lazy val? So we are going to talk about lazy val right now, but this is what goes with call by name, something called a lazy val. So what's a lazy val? So a lazy val is something that's going to have the same semantics. It's only going to be evaluated when it's actually needed. So here is the idea. So let me call this a lazy val and a lazy val. And then comes the kicker. So suppose now I have made these lazy. Let me call my function again. And here's what you will see. You will see that G of 10 is evaluated, but you will see that G of 12 is never evaluated. Okay, here it goes. G of 10 is evaluated, but G of 12 is never evaluated. See, no G of 12, no G of 12. And the reason is, when I make it lazy, what happens is, let me show you. Let me show you. So let's say lazy val y equals G of 12. All right. So, and then let's say print line, let me rest, take a nap, do some computation slowly. Okay. And then let's say, let's print y. So here's what's going to happen. Aha, yes. So that's exactly it. So let us talk in terms of this example, right? Let's talk in terms of this example, right? So when I declared y to be a lazy val, then G of 12 is not immediately evaluated. Okay, so I'm going to answer John's question just now. Okay, it's not going to be immediately evaluated. What you're going to do is you're going to hold on until you actually need it. But remember, when I'm printing, I will actually need the value, because I don't know how to print 13 without actually computing it. So notice here that the first print statement is this: let me rest, take a nap, do some computation. And then I call G of 12, and then I print 13. Okay, suppose I did it a second time, and suppose I did it a third time. Do you think G of 12 is going to be called the second time and the third time? The answer is no. So this is what happens. And in fact, you can see y is int is a value called lazy. So if you can see this, yes, it is a val, but what happens is it memoizes. So lazy val also memoizes. So what does memoize mean? Memoize means that when I actually compute, so here G of 12 is actually computed. So y becomes memoized to 13. So when you first time you encounter a use of y becomes memoized and it becomes its actual value 13. So in the second time and the third time, you don't have to go back to what it used to be and compute it. It's already 13. So under the hood, a lazy value, the first time it's computed, the second time or the third time it gets memoized and it's not recomputed. And this is how a lazy val works. Okay, and there is no such thing as a lazy var, because when you have side effects, you can't do these things. Okay, so if you try something like a lazy var, lazy not allowed here. Only vals can be lazy. Okay, so only vals can be lazy. Vars cannot be lazy. Yes. So Evan, your intuition is absolutely correct. If you have side effects in the function g, then this is going to not give you the correct result, or you have to be very careful in how you reason about the side effects. If you have side effects in G, forget about it. This is not going to work well. This works only when you're purely functional, which means you program without side effects. Yes, so Sean, this is exactly like memoizing for dynamic programming or caching. It's a way where if you have previously computed a value, you keep it, you store it, so that the next time you want the same value, you look it up from the table. And that's exactly how it's done. It's a form of memoization. So lazy val, you memorize. So the first time you assign y to g of 12, y is not evaluated. Y is just the expression g of 12, the function called g on the argument 12. And then you do some work, and y doesn't change. Y is still g of 12. But the moment you need the value of y for some other computation, let's say you needed val z equals y times y, something like that. So now you're going to have to compute y. On the other hand, if it were lazy val, you're still not going to bother. You're still going to keep it lazy. And you're only going to compute it when you're going to need Z. All right. So the point is lazy evaluation. The principle is that you only compute things when you actually need it. Good so far? And you have to be careful in lazy evaluation that when you are using call by name like this, call by name, which is lazy evaluation at the arguments of a function call. So call by name is how parameters of a function call are being passed in a lazy evaluation style. The other thing you have in Scala is this lazy val or this lazy let binding. When you do a lazy let binding, you have to make sure that whatever your let binding has no side effects, because you're going to memorize and you're not going to keep running it again and again. So whereas on the other hand, call by name does not memorize. So when you call X by name, this doesn't memorize. Every time you try and access X, it's going to evaluate whatever expression you was afresh every time you want to do it. Okay, so far? In other words, if X were G of 10, it's like substituting G of 10 everywhere you see an X. And that's why it's called call by name. In some sense, you're just doing a substitution. Wherever you see X, replace it by that expression syntactically and then evaluate it. Good so far? Does this make sense? Okay, very good. Now let me talk about lazy. Why do we need laziness, right? So there are many reasons you need laziness, right? So you would think the reason you want laziness is, so I'm writing up notes. I'm almost done. I'll post it as soon as this class is over, after I give you some more things, right? So the reason you need laziness, there are a couple of reasons you need laziness. Yes, so Cedric, Scala does type check lazy objects. So in terms of type systems, you pretend that the lazy object has the same type it will be when it's evaluated. So even though this is a lazy or a call by name evaluation, I'm not going to be worried about its type because it's going to be an int. Okay, under the hood, the runtime system has the difficult job of maintaining that it's G of 10, remembering what G is, keeping that closure, remembering that argument is 10, keeping all of that delayed computation up there, and then running it when you need it. So that headache is purely the compilers. As far as you are concerned, the type system does not change. It's still going to be as if it were called by value. You can still reason about it like that. Nothing changes there. Thankfully, because you don't have side effects, right? If you do have side effects, then obviously it's not going to be the same. I can do some weird things by assignments and side effects and all sorts of those kinds of things. So that gets very complicated, weird. So typically languages where laziness is first class, like Haskell, or pure functional languages. So in Haskell, you don't have the notion. You do have the notion of state and mutables, but for that you have to use something called a monad. And that's the pure functional language's answer to how to deal with state. And if you go to this book called Learn You a Haskell, there is a chapter called A Fistful of Monads, which is a really fun chapter. You can read through it, but you have to read a bit of Haskell to understand it. Okay, so the concept is called monads, but that's how you do it. But let's not get into side effects and all of these things in lazy languages. That's an advanced topic, hopefully for a graduate class. Okay, let me talk about why we need something lazy or call by name, for example. So it turns out that a lot of times we build what are called domain specific languages. We can build our own cool bit of syntax. So here's my while loop. So this is an example of a while loop that I have implemented using lazy functional, using a call by name. So take a look at this. So it says, this is my while loop. There is a condition B, which is a Boolean, but it's a call by name Boolean. Okay. And there is a body, which is a unit, but it's a call by name unit. And the whole thing returns a unit. And it says, if the condition B holds, then uh, evaluate the body. And by the way, after the body, recursively call my while loop with the condition B and body. Okay. So normally this wouldn't work. So normally this wouldn't work if this weren't called by name. But because this is called by name, something cool happens. What happens is I can write while loops now like this. So I can say my while loop I less than equal to 10. So this is the Boolean B, okay, where I is my var. So I've defined I, initialized it to 0. So while I less than equal to 10, this is what I do. I equals I plus 1 and print I. So this is what I do. And this is my body. So this is my body. It's a caret function. So this is my body. This is my body. And here's what is cool about it. Because I'm doing call by name, none of these parameters are actually evaluated. If they were evaluated as in call by value, this would have become my while loop of true, and I equals I plus 1. This would have evaluated just once, and it would have become unit. So if I had let them evaluate, then the game is done. I can't do anymore. And then the loop is just an infinite loop because B is always true. But that's not what it is. It's like B is not being passed as the value of I less than equal to 10. It's the expression I less than equal to 10. That's what B is. The body is not the value that's produced by running this. It's this expression itself goes into the body. And now look at this. So every time I check it, so when I check it, I'm going to evaluate I less than equal to 10. Now I'm going to run the body. But then again, I recursively call it. Again, it's called by name. So the B and the body go back. So this executes just like our honest to goodness while loop and produces an answer just like our honest to goodness while loop. So interestingly, some cool bits of functionality get enabled that wouldn't have happened without having call by name. There is no way to do it without call by name. So I can do certain things very nicely. So in fact, with call by name, I can implement my continuation passing style and trampolines in a different manner. So there are some cool things I can do there. Okay, won't get into the details, but with lazy evaluation and call by name, that stuff gets very nice as well. Good so far? All right. So the other thing that we do with lazy evaluation, and this is why lazy evaluation is something we have to take seriously, is lazy data structures. So turns out data structures, the way we have learned data structures so far are all eager. So what happens if you allow laziness in your data structures? All right. And so you get some very, very cool kinds of data structures with lazy data structures. And I'll talk about just one, which is, in fact, it's the only one that I have seen very commonly used. And it's called a stream. All right. So what is a stream? So a stream, and by the way, I think Scala is deprecating the term stream and starting Scala. So starting Scala 22.13, which is the Scala version that's the latest. I think these are called lazy list. Okay, so the latest version of stream is called lazy list. But however, my Jupyter notebook, our Jupyter notebooks are based on 2.12, and so it's still called stream. Okay, so it's still called stream. So let me talk about streams. So what's a stream? So a stream is exactly like a list. So you can declare a stream, let's say of int, and you can say it's a stream of 1, 2, 3, 4, 5, 6. So that's an example of a stream. So it's exactly like a list. You can type a stream of strings. You can just type go with the flow, something like that. So this is an example of a stream. Yes, so almost right. So you're almost right, Kai. That a stream is in the sense of C++ in an IO stream kind of a thing. All right, uh, except that a Scala stream does something, allows us to do some really cool things. So let's talk about what streams allow us to do. But it's the same idea. It's like a stream is basically like a bunch of data where you can keep asking for more and more and more things until you get to the end of the stream. Okay, so it's like a sequence of data that comes forth. All right. Now, except that whereas you built lists like this, so whereas you built a list using the cons operator, okay, a stream is built using the stream cons operator. So I just say this. And then instead of nil, I say stream.empty. Okay, so instead of the cons operator, a stream is built using the stream cons operator, which is the hash : operator. Okay, and that's in Scala, that's the stream cons operator. That's the cons for stream. All right. Now here comes the really cool thing. So let's go back to this function g. So g is this silly little function that's just going to uh, yes, it's actually very similar to a generator in Python, though I will show you a different concept called an iterator that's going to be an analogy to generator. Okay, so a stream is actually even cooler than that. So I'll talk about that, but it's the same idea. You're getting to the same idea, right? So you're getting to the same idea of a generator. All right, these are all related ideas. So let me show you the cool thing though. Let me write a stream like this. So let me write a list like this. So list is g of 10, uh, const with g of 11, const with g of 12, const with g of 13, const with nil. Okay, I'm going to press enter. Anyone willing to predict how many times g is going to be called when I press enter? 4 times. 4 times. I'm still not lazy, right? This is eager. This is the eager world. Okay, yeah, so don't get too far ahead, right? But what happens if I do a stream? So here's what happens. By the way, this effect, you're not going to be able to see this effect for a bit. So let me actually explain a little bit of a bummer that's going to happen. And I'll explain what's happening. Okay, so let's do this. And let me write some other stuff. Let's say print line str. Okay, so let me just print it and print line computation done. Because there is something that I don't like that the kernel does to us, which kills the effect. But remember, I've created this stream. I've created the stream. I'm printing the stream, and then I'm printing computation done, so that you know when the computation is done. So here's what happens. Okay, so let's watch until computation done. And I'll explain this strange thing. It's actually an artifact of the fact that we are using Jupyter. But here is the thing. When I create this stream, it turns out that the only thing that it calls is g of 10, the very first element. So it's stream 11. And look at this, it says question mark. So what it means is that it does not bother materializing the rest of the stream. So only the head of the stream is materialized. The rest of the stream is not going to be materialized, and the computation is done. Okay. Now I can say print line stream.head. So that prints the first one. I can say print line stream.tail.head. So that's going to print the second element. I can say print line stream.take take 3. So take is a function that's going to take the first k elements, whatever the number here is, that's going to print that many elements. Okay, so these are examples of operating with streams. And as you will see, the values of the elements of the stream are only computed when they are needed. So when I print g of 10, so when I print the head of the stream, I'm going to call 11. So when I print the tail dot head, I'm going to get g of 11. Okay, so here is the cool thing, right? So when I print stream dot take 3, I just get stream of 11. So here is the cool thing, right? Computation is only achieved when I need the result. So when I say print stream.take3.toList, this is the function that converts a stream into a list. You will see that list of 11, 12, 13 is printed. And now G of 12 is called. So it turns out things are being called on demand. When I need them, the elements of the list are being materialized. So it's almost like a lazy list, a list whose elements are lazy, which means that I am not going to bother computing these elements until I actually need these elements. I am not going to compute them. I'm just going to just pretend they exist, but I will come to it when I need it. Now, obviously, look at these functions on streams. So you can take stream.head, which is the first element of the stream, stream.tail, which is the rest of the stream. So you can talk about stream.tail.head. So very much the same functions that are enabled on a list are also enabled on a stream. So you can also say stream print line stream.map x maps to x times 2. So you can do print line stream.filter x arrow x percent 2 equals 0. So this is like multiply all elements by 2, or filter all even elements. No, so this is the cool thing, Kai. You will never be able to see the length of the stream. You could, but for that you have to convert the entire stream to a list, which is dangerous. As you're going to see, the length of a stream is not something I will ever try to find out. Like it's not something I imagine that has a definite end. It's something that I imagine could just keep going. Like I could keep asking for more and more and more things, and the stream could just keep providing me more and more things. So a stream is a very strange data structure, but it's a lazy data structure. Okay. Interestingly, when I do stream.map x arrow x star 2, so let me call this double stream. Okay. Val double stream equals stream.map x arrow x star 2. What you will see here is that this is not going to run map. It's simply going to create a new stream. I will only produce the elements of the stream when I need it. So let's comment out all of these things. Let's just directly go to stream.map. As you will see, it's not going to do a map. It's not going to run this function. In fact, let me, while doing map, let me just do a print statement before the map. So let's print map. Okay, so I'm just inserting a print statement just to show that when I'm running the map. Likewise, let me insert a print statement just to show print line filter, just to show that I'm doing a filter. Okay, so and let's call this filter stream. Now, obviously, what will happen is this. Okay, so let's call this filter stream. Okay, and watch there is I have placed a computation done here because there is some stuff that happens after the computation is done, and I'll tell you what's happening there. Uh, so just watch until this, right? Uh, when I call stream.map, notice that there is just one, even though the stream has 1, 2, 3, 4, 5 elements, right? 1, 2, 3, 4 elements. Map is just this inner function is just being called once, because what Scala does as a rule is it always keeps the first element of the stream. So that way it knows whether the stream is empty or it has something in it. So you don't know the length of the stream, but Scala tries to assure itself that it's not an empty stream, that there is something in it. So it evaluates until there is a first element. So when I call stream.map, it calls g of 10, it produces the first element of this double stream. Okay, so in fact, if I print double stream, you will see that. So if I print this stream, double stream, double stream equals dollar double stream, you will see that Scala will have the very first element and then it doesn't know. Okay, so it says double stream is stream 22 and I don't know what. Likewise, let me print filter stream, right? Uh, print line filter stream. Everyone with me? Any questions? This is absolutely the coolest part of functional programming. And I'm so sorry that we are getting to this at the very end, but this is an advanced topic. It's going to be confusing and it's hard to reason about. And you have to learn all of this functional programming before you're ready for this. But this is absolutely like you're getting to like black belt functional programming. So map and filter will pass all unknown elements until the first unknown element. Yes, exactly. So here's what happens. So you can see that map is going to produce a stream, stream 22, and filter is going to produce a stream, stream 12, but it doesn't bother processing the rest. It's just question mark. Question mark means like it's stuff that I haven't processed, stuff that's still left over as lazy computation to be done. But notice here, filter is being called twice. So the function for filter is being called twice. Why twice? Yes. So Kai's answer is exactly correct because the first element is odd, right? So it skips over the first element. And remember, Scala tries to evaluate a stream until it finds a first element. So it will get to here. Okay. Now, I've stopped the computation here, but notice what happens here. This is an annoyance. So after this, why is all of this being called? Because of this. Because turns out Almond likes to print stuff, and because Almond likes to print stuff, the Jupyter kernel likes to print stuff. The lazy computation effect is killed out because once it wants to do this print message, the lazy computation is no longer lazy. It makes it all eager and goes ahead and prints everything. Okay, so that's a bummer. So that's why I printed this computation done because it's going to have force you to print all of this. Okay, so that's unfortunate. The way to get rid of it is by declaring it lazy. You can make Almond behave a little bit better. So by declaring these streams lazy, Almond behaves a little bit better. Okay, so now it doesn't print the streams, it just prints lazy, 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 and you get the same answer. So sometimes you will see me declare it as lazy for no good reason. That's why I declare it as lazy, so that I can get the Jupyter kernel not to print it. Okay, so far? Everyone okay with stream? Why would we use a stream? So what would be a good use for a stream? In fact, there are many, many, many great uses for a stream. Let me show you one pattern that's very, very common where you should use a stream. Okay, so the nice thing that happens with a stream, is let's do some task like this. This is really, really common. Load a file from a disk, go through each line in the file, match against some pattern, let's say a regular expression pattern or something like that. If it matches, print that line. Uh, and if more than 10 lines have been printed, then exit. So let's say I want to load a file from a disk, and get you the first 10 lines of the file that match some regular expression pattern. Is that okay? So this is really, really common. You take a file, you go through each and every line of the file, you do some pattern match, and let's say I want to print the first 10 values of the pattern match. All right. So normally you should not need to load the entire file and process the entire file just to get the first 10 pattern matches, right? So let's see how we do it, right? So here is how we do it. So here is the eager way to process a file. So this is called process file eager. So F is the name of the file, and it prints a list of the lines in the file. So a list of string. Okay. So I use a Scala library called scala.io.source. So what I do is I load the file by calling source.fromFileF. So that loads the file. All right. Uh, I use get lines, and that gets all the lines from the file. Uh, I convert those lines to a list, and I apply a filter to the list of lines. I apply my filter. So my filter takes a line like a string, which is a single line of the file. And let's say it applies some regular expression, but here I've just applied some such, some pattern. All right. So it says the length of the line is greater than equal to 10, and the line does not contain dot. It could be some regular expression pattern that you are interested in. And I'm also counting how many times this filter method got run. So that is num filter apps. I'm just doing some statistics. So do some statistics. Good so far? So I'm just doing some stats on how many times this function got called. Otherwise, you don't need this num filter apps. Uh, and then finally, the last line is dot take 10. So take 10 from a list means take the first 10 elements of a list. All right. And I have a file called War and Peace. So I downloaded the famous novel War and Peace by Leo Tolstoy. And from online, it's available for free. And it's a great novel. You can read it. And I just want to know how many times the filter was called. Okay. So here it turns out in this eager evaluation, the filter is called with as many lines as there are in War and Peace. So 77,788 lines. All right. So this is what happens when you do this, right? Uh, good so far? This is nothing, nothing great. This is how you would do it from everything I've taught you so far. You're using functors instead of using loops. Okay. On the other hand, let us see how we do it using a stream. So here's how we do it using a stream. So suppose I, instead of doing it, converting the files to a list of lines, what happens if I convert the file to a stream of lines? So now what happens is when I convert it to a stream, I get lazy evaluation. So this part, the highlighted part, is done in a lazy fashion using stream computation. So now if you look at how many times filter was called, it was just called 27 times instead of 77,788 times. And why is the reason it's called 27 times? And the reason is when I convert it to a stream, then all of these become lazy applications. All of these become lazy applications until I get the final list. And the answer is exactly the same. So you get exactly the same answer, but the filter method, when I convert it to a stream instead of to a list, it does lazy processing. So this is a pattern. It's a pattern that's very commonly used. So remember, stream processing is done lazily in Scala. So you gain a lot. You gain a lot when you do things like this. So it gives you this idea of a pipeline. It gives you this idea of a pipeline where you're passing data through methods and getting to the end. Okay. So that's one good reason to do streams. The other good reason is you can do some very atrocious things with streams, which cannot be done any other way, and these are called infinite streams. So you can create some very crazy kinds of streams like this. So you can say define infinite stream of ones equals. So this is a function, uh, let's say, that returns stream of integer equals, let's say, it's one stream concat stream const with infinite stream of ones. So I can write something like this. I can say an infinite stream of ones is a one stream concat with infinite stream of ones. If you did the same thing with a list, infinite list of ones, I don't need the open bracket, close bracket, okay? That's not needed in Scala. Okay, so here is the infinite stream of ones. Again, I don't need open brackets, close brackets. I can get rid of that. This will actually terminate. And if I did this, val s equals int stream of ones. So this actually terminates. Even though Almond likes to print it, even Almond at some point runs and says dot, dot, dot. It's not going to print it anymore. It tries to unwind the stream of up to some fixed length and then it stops, okay? So this is how an infinite stream of ones works. What about this function? Do I dare run it? Should I run it? Yeah, I shouldn't. I would crash because this is going to go into an infinite loop. Again, this did not go into an infinite loop. Why? Why did this not go into an infinite loop? Yes, so that's exactly right. It evaluates only the first element of the string. So what it does is Scala will evaluate the first element, which is one, and the rest of it is just unfinished computation. It's just computation that's unfinished. So that's where it's going to be. So you can do some crazy things with this, right? So what can you do, right? So you can do some very cool generators. So let me write this program, which is all Fibonacci numbers. It's a stream of integers. Okay, so let me have two arguments, x1 colon int, x2 colon int equals x1 stream concat all Fibonacci all Fibonacci stream x2 x1 plus x2. So this is a very slick definition. Hold on, I need to write the type. So this is a very slick definition that's going to encode all Fibonacci numbers. And then you can say val Fibonacci stream equals all Fibonacci stream. Let me call that on x1 equals 1 and x2 equals 1, which are the first two Fibonacci numbers. And so it says is the stream of all Fibonacci numbers with x1 and x2 as the current values is going to be the value x1 stream concat with all Fibonacci numbers with x2 as my new x1 and x1 plus x2 as my new x2. So this is just sneakily doing the Fibonacci recursion. It's just saying I carry two numbers around. The second number becomes the first number, or the first number becomes the second number, and the second number becomes the sum of the previous two numbers, right? So this is just carrying the two consecutive Fibonacci terms, right? And then I put one of the terms in the stream and just advance the recursion forward. Okay, and this produces all Fibonacci numbers, and then I can say val fib numbers, first 100 numbers equals fibstream dot take 100. So that's the first 100 numbers. Then I can say val numbers until 1 million equals fibstream dot take until or take while x arrow x less than equal to 1 million. So this is going to extract elements into the stream from the stream while this condition holds. So while the number is less than this 1 billion or one, this is 1 billion, I guess. While the number is less than 1 billion, it's going to keep taking numbers from the stream. This is going to take the first number, 100 numbers from the stream. And of course, I'll convert it to a list because otherwise it won't be printed. It will still remain lazy. So this is what happens then. So, so now fibstream is this lazy stream, but the first 100 Fibonacci numbers are printed, and then numbers until 1 billion are printed. So this is the interesting part where normally this would be an infinite loop, but because I'm using streams, it's not an infinite loop. It does something lazy. So I can do some really cool things with lazy computation, but I have to make sure that they remain lazy. For example, if I did this fibstream.toList, then I'm done for, because this is going to run forever. If I try to convert it to a list, it will run forever. So you have to be careful how you work with streams, because remember, streams, you don't know how long they are, and potentially they could go forever. Good so far? Okay, if that's good, so I talk about infinite streams. All right. So as an alternative to streams, there is something called an iterator, which is very close to the notion of a generator in Python. Okay, so an iterator is actually a trait. It's a trait in Scala that expects us to implement two methods, next and has next. So let me implement a simple iterator. And this iterator is called a range iterator. So it's an iterator with a starting value, an ending value, and a step. Usually the step is defaulted to 1. And I say it extends an iterator of type int. Okay. And because it extends an iterator of type int, I have to create two functions. I have to create a function called hasNext, and I have to create a function called next. The function hasNext tells us whether the iterator is ended. So I override this and I say define hasNext, which is a Boolean. And this says the current value of the iterator. So I have to store some state. So current value of the iterator is strictly less than the ending value. Okay, and that's the function hasNext. And the function next is the function where I'm going to compute the next value of the iterator. So what I'm going to do is I store the current value of the iterator. I increment the current value by the step. So in fact, this only works if step is greater than 0, and I have to assert that start value is less than or equal to the end value. So those are two things that are needed. Okay, so now the current value is incremented by the step, and I return the old current value. So this is the next. So this is how I get to the next element of the iterator. So as an example, I can create a new range of numbers from 100 to 142 with a step of 5. So I can create a new range. So this is a new range. And I can convert the range to a list. So this function list is inbuilt. So toList is inbuilt in the iterator trait. So I can use the function toList. And as you can expect, this will become 100, 105, 110, all the way up to 140. Good. But if I tried it again, if I tried r1.toList again, I will get the empty list. Can you explain why I get the empty list the second time around? Yes, so the iterator is exhausted. All right. So an iterator is a mutable thing. So it has mutable states. It's using mutables or var inside it. So once I run through a full iterator, if I don't reset it somehow to the beginning, it's going to be exhausted. All right. On the other hand, I can provide exactly the same functionality using a stream. So here is how I provide it using a stream. So I define a function called stream range, which has a start, which has an end, which has a step. Okay. And instead of producing iterator, it's producing a stream. So how does it produce a stream? So it says if start is less than end, then place the starting value, uh, stream concatenated with recursively calling stream range. Now, but instead of start, I say start plus step, end step. So this is going to be how I'm going to do that. If the start is already greater than end, then it's the empty stream. So this is how I define stream range. So this is interesting. So it provides me the same functionality as this iterator, but it's the immutable version. It's the pure functional version where I don't do the mutables. I use immutables all around. And here you can see I can create a stream range, the same stream range from 100 to 142 with a step of 5. I can convert it to a list. But the nice thing is because it's immutable, I can keep doing it again and again and again. So because it's immutable, it doesn't exhaust itself. It just keeps running again and again. Okay, so far? So similarly, here is I remember I created an iterator of all Fibonacci, a stream of all Fibonacci numbers. Here is the iterator for all Fibonacci numbers. So I create a class called all Fibonacci, which extends the iterator. Inside the class, I store F1 and F2, which are the two previous Fibonacci numbers. Okay. And if you ask me to give me the next value, you don't need that bracket here. Then I can say temp is F1 plus F2. F1 is F2, F2 is temp. So I update the Fibonacci state and I just return F1. Okay. And has next is always going to be true because this is an infinite stream. I always have a next Fibonacci number. So I just return true here. So this is my example of a stream of all Fibonacci. And again, the function take is defined in the iterator. So it's already defined for iterators. So I can say create all Fibonacci iterator, take the first 1,000 and convert it to a list, or take the first 1,000, map it to hello plus dot string dot to list. So you can do all of these cool things. And in the second case, you get the string appended, hello appended. Okay, so that's an example of an iterator, and that's very much like a generator. Okay, so what are the key differences between a stream and an iterator? So the main difference is a stream is immutable. So we can we can iterate over a stream multiple times. There is no notion of a stream being exhausted. You can always go through a stream again and again and again. That's nice. An iterator is typically mutable. Okay, typically the way you implement an iterator, you have to keep an internal state and you have to change the internal state every time you call next on an iterator. Okay, and typically it's meant for iterating exactly once and not again. All right. Last thing is streams support memoization, whereas an iterator does not. So if I reiterate over a stream, or if I go over a stream again, then I have memoization. So what's going to happen is that the values that are computed are stored in the memory. So it's not going to recompute those values somehow. Whereas in an iterator, if I reset it, then I have to recompute the values all over from the beginning. There's no notion of memoization. Okay, so far? All right. So I assume this is okay. So there is a last bit I wanted to talk about, but I may be out of time. So I may revisit this topic towards the end for the very last lecture. And this topic is the topic of for loops or comprehension. Okay, so I wanted to talk about this because the way we have covered for loops so far has not done justice to for loops. So we have to go back and re-examine for loops. And so what's the idea here? So we've seen for loops before, right? So we saw this kind of pattern. Here is a for loop to sum up the first 20 elements, right? The first 20 numbers. So you create a var called I. You iterate j from 1 to 20. and you say I equals I plus j, you accumulate, so you are accumulating, and then you print the sum, and you get the sum as 210. So this is nothing surprising, right? The same for loop in C++ would be this: int I equals 0, int j equals 0, for j equals 0 to 20, j less than 20, j plus plus. So this would be the equivalent for loop in C++. However, the simple thing is that the for loop in C++ has a different meaning, completely different meaning than the for loop in Scala. And this is actually true in Python as well. The for loop in C++ is completely different from the for loop in Python. So here is an example. So you say int j equals 0 for j equals 0, j less than 20, j plus plus, same thing. But inside the loop, you keep setting j to 0. So what happens when you run a loop like this in C++? Infinite loop, right? Clear, never ends. What happens when you run a loop like this in Scala? Very good. Error, because you're not allowed to reassign this because it says reassignment to a val. So this is really surprising, right? J is actually a val uh, in this for loop. But on the other hand, j goes from 0 to 20. How can a val go from 0 to 20, right? Isn't that confusing? Okay, here is the other. Let's write a different for loop here. Okay, this is an even more crazier for loop. So here, I define a var called n equals 10, okay? And I say for j from 0 to 10, n equals n plus 1 and loop. So now I increment the outer boundary of the loop as the loop goes on. Do you agree that this is an infinite loop? On the other hand, it's not. It actually finishes. It runs in 20 steps and finishes. So what's happening here? Yes, but j increases by 1 each time and n increases by 1, but this loop still finishes. It actually finishes in 11 steps. So what's happening? So this is what is happening. So by the way, let me show, let me leave this as a, yes, so Cedric, you're right. It makes a copy of n and keeps that copy of n. In fact, let me show you the, I have a couple of more minutes. So let me show you the Python, right? What happens in Python. And then I will try and cover this next lecture and try and demystify this, right? So let's take Python. Sorry, let's do. All right, so let's take Python. All right, let's write this for loop in Python. So I can say for I in range 0, 10, I equals 0, print line, sorry, print loop. Oh, wait, hold on. It's not showing. Hold on, let me share again. Can you see now? So in Python, I'm just running a loop from 0 to 10, but I'm taking the loop counter and making it into 0 every time. And I'm just printing, right? So get ready for an infinite loop, right? Hold on. Oops, sorry. For I in range 0, 10. Oh, that actually finishes in 10 steps. So also, that also finishes. So not only is this a feature of Scala, the same thing happens in Python. All right. So I will let you figure this out. I will post my notes, which will demystify why this is happening. And the reason this is happening is twofold. One is that this value of n gets captured the first time you evaluate range 0n. So range 0n is an iterator object. So what happens then is n gets plugged into 10 the very first time you create this range, and that's what it is. And the second thing is this I is not like a loop variable the same way as C. What it does is every time I just gets a new value from this range object. So no matter, even though you mutate n here or you mutate I here, when you get back to the head of the loop, you just ask for the next element in the range. Okay, so this is how generators or iterators work, and I will explain this in the next lecture, and I'll show you what's happening in Scala as well. Okay, so in the meantime, have a great Thanksgiving, and thank you everyone. Yeah, see you next week on Tuesday. No lecture on Thursday. Yep, thank you.